Suppose we have a bacteria that reproduces by division. If we start with 1, then the next generation we would have 2, right? Because it splits in half. Then these 2 would each divide in the next generation to give us 4, and then 8, etc. Now notice how these counts are all powers of 2, right? Starting with 2 to the 0, 2 to the first, 2 squared, and 2 to the third. So we could generalize this if we wanted to keep going out to the nth generation as 2 to the n. Now finally, we could turn this into a formula by associating each generation's size with the corresponding generation number, right? And if we did that, we would get f of n equals 2 to the n. And we need to specify where we start here, right? So I would say n greater than or equal to 0. Okay, so what makes this function unique and brings it into the discrete math category is that the domain of the function is just positive integers, because you really can't have a fraction of a generation. So our function from the previous slide is an example, a specific example of a class of functions called sequences. Right? These functions, now they're the same things that you're familiar with from your algebra classes, except the domain is limited to integers, either a finite set, all the integers between two numbers, or an infinite set where the domain is all of the integers greater than a fixed value. Now notice here that while the domain can be infinite, the way the definition is worded, the domain will always have a minimum value. That's because we strictly said greater than here, right? So our sequences, they're always going to have a well-defined starting point or an initial value. So while we can always use that familiar function notation to define a sequence, a more common approach is to define a sequence in terms of its nth element, like I've done here. Each element of the sequence is called a term, and the initial term and the endpoints are called the initial term, or sometimes the initial value. And the last one is the final term, or again, sometimes you'll see it called the final value. Now, keep in mind that that final term might not exist. Right? That was the second case in our definition, where there wasn't an upper bound. Okay, so in that case, we would have an infinite sequence, and we would note that just by leaving that final term off and ending with ending the sequence with ellipses. And finally, notice that I haven't specified an initial value. Right? In mathematics, our sequences will generally start at 1, since that's how we count things. But other fields may do things differently. Computer science, for example, generally starts lists at 0 because binary 00000 is 0 as a decimal value. So that's a logical place for computers to start thinking about a sequence. And there are also going to be specific scenarios where we need a sequence to start at some other number. For example, if our sequence represents the size of a city's population, then our initial value could be the number of the starting year in our study, for example. Okay, so I've got a specific example of a sequence here for us to look at. And what I want you to do is try coming up with the first 6 terms in the series. Right? Then we'll come back and we'll go over them together. Okay, the inequality on the right tells us that our sequence is going to start at n equals 2. and we want 6 terms. So we're going to need to calculate a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, and a sub 7. So to find the specific values, we'll substitute the indices, the 2, 3, 4, 5, 6, and 7, into the formula. And so that's going to give us, for example, for this first one, that would be 8. For the second one, I'm putting 3 in here. For the n, that's negative 11. And if you keep doing this, you should get 14, negative 17, 20, and negative 23. Now, notice what effect the minus 1 to the n part here at the beginning had on the results. It made the signs of each term alternate, giving us what's called an alternating series, alternating sequence. So mathematicians never wants to leave well enough alone. Are going to take this a step further, right? If we can write out all of the numbers in a sequence using a formula this way, well, can we add them all up? Right? And if we do, okay, then what happens? All right, if we take all the terms in a sequence and add them up, what we get is something called a series. And that's what we're going to talk about in the next lecture.